So welcome back, everybody. Looks like we find a good solution. So what I'm gonna do today is to talk to everybody about what we're gonna do in today's lecture regarding the phase diagram of the polymer solution. In the last lecture, we discussed the polymer solution in terms of osmotic pressure, and I think the homework we have two of those, and many of you had a good grasp about what is osmotic pressure is, where is the origin of the osmotic pressure based on the polymer concentration as well as molecular weight. So what we're going to do in today's lecture, we're going to wrap up in the osmotic pressure part. I left something for everybody to think about. What is the link between the osmotic pressure as well as the Flory-Huggins theory? We have discussed the Flory-Huggins theory quite a lot, and this is going to be the first application of the Flory-Huggins series, and that is how we can link the osmotic pressure to the Flory-Huggins theory. Okay, so we're going to use about 5 to 10 minutes to wrap that up. Then more importantly, in today's lecture, we're going to talk about the phase diagram. So the phase diagram is a process that everybody should know. It talks about how the polymer behave at different concentration. Will the polymer and solvent mix or not? And the criteria is quite clear, as we talked about the lattice theory, Flory-Huggins theory, if the delta G or free energy will be reduced if we mix the solvents. The outcome would be either going to be mix or not mix, and this depends on two different parameters, as we will talk about in more detail. It depends on temperature, it depends on the composition. Okay, so hopefully we will be able to cover most of the second half in terms of phase diagram, and everybody has some knowledge about what is phase diagram is. And we likely going to take one more lecture on the phase diagram because it's a very important and in-depth topic. Okay, so where we left from in the last lecture is I left a question for everybody to think about: how can we use osmotic pressure in the relationship with Flory-Huggins theory to understand them. So the answer is quite simple. We define what is chemical potential in terms of polymer as well as solvent. It's just a partial derivative of delta G. Use a molar volume, so a molar ratio, right? So this is going to be delta G, partial derivative of N. N is how number moles of your polymer or molecular. So you can see this is a classic Flory-Huggins equation, as everybody knows. That delta G equals to RT and 1 log phi 1 and 2 log phi 2 and N1 phi 2 chi. And now the how do you link the Flory-Huggins theory to our osmotic pressure is quite straightforward. We just need to understand what is this partial derivative. So we take the, delta G, take a derivative of partial delta N, then we will be able to get what is chemical potential for each species. And what we need to do is to get what this value before and after we mix it. And that's the difference where you need to get before mix and you need to get value after mix. Okay, and I'm not going to spend quite a long time to go through all the details. I will set up a separate session as a supplement, as like I did in the previous lecture, as a supplement for these in-depth derivative and mass operation. If you are interested, feel free to go into that. But essentially what we're going to be able to reach using that, I'll quickly use a minute or two to show everybody what would be look like. So what we need to do is to take a derivative of what is different parameter in terms of osmotic pressure divided by RT, and that is quite straightforward. We just need to consider delta G M divided by partial derivative of N1. So what is GM? What is N1? Those we have been defined in the past, right? So essentially, what you need to do is to take a partial derivative for the long equation I showed. It's going to be RT N1 log in phi 1 plus N2 log in phi 2 plus N1 phi 2 chi. Okay, then you need to take partial derivative of N1. So if you do the math correctly, you will see that N2 phi 2 and phi 1 phi 2 are all related to N2. So if you do, sorry, this actually should be N1. If you do a partial derivative of that, you would be able to link everything to what is N1 is. For example, if you run the math correctly, I would just show one example. This phi 1 partial derivative N1 will be ended up as phi 1, phi 2, and N1. And you will see, similarly, you can expand to what is phi 2. So essentially, you can take a partial derivative of delta G to all these different components and arrive at a conclusion what this will be. So I'll let everybody know the detail. So this will be V1 phi 2 divided by N minus, so this is a chi minus half, then phi 2 square. So using the Flory-Hagen theory, so this is what you will be able to reach. And if you were able to take one more step and further simplify what is phi 2 and how it relates to what the value we know, volume concentration again is this is a volume fraction is equals to concentration volume, molar volume, or each unit volume divided by n. You will be able to reach a very simple equation that you would have C concentration in V1 and so what we are doing now is trying to further replace this phi 2 term to a very common concentration and n term. You would be able to reach what is n using a very simple derivative of the Flory-Hagen theory. This is what you would get. You would get osmotic pressure will be equals to this long equation. But if you recall what we talked about in the past, osmotic pressure, we can also understand this as, so let me use what we have used. Second Vary coefficient, third Vary coefficient, and compared to the Taylor expansion method, right? And you will see this is top row is Flory-Hagen theory. The second row is a conventional approach where we use the Taylor expansion approach. And comparing these two, you see the first term is basically the same. The second term is slightly different, but they are also comparable, right? So in this case, V2, or second Vary coefficient, you can reach it to the conclusion it will be equals to particularly this term. And these are the unit volume, V1, and this is going to be the related to the molecular parameter. Molecular N is a degree of parameterization in molecular weight. And what is more important is V2 is proportional to half minus chi. And as we defined in the last lecture, we know the V2, if it's equals to 0, that means it's a Seder solvent.
Dr. Gu?
Yeah? You have a question?
I think his mic muted again, or like it went back and muted, but on YouTube the like audio is cutting out like really bad. Like it just like goes in and comes out.
Okay, let me check.
Like it's fine here, but it's like it's so delayed that you'll say something now, and then we won't see you write it for like 30 seconds.
Okay, that seems a problem. When we try something new, there seems always going to be something came up. Let me see what we can do. So there is a problem that audio sometimes cut, or is a problem that the audio and video are not synced?
It's
I was going to say it's twofold, right? Because the audio on Zoom is good, but we can't watch the YouTube lecture with the Zoom audio, and the YouTube audio is really bad. Cuts out every couple of seconds.
Okay. I think then we need to make a decision for the class. Looks like this first try solved partially the problem that the now we have.
Go back to pre-recorded lectures and then meeting in the last 15 minutes of class.
Is that everybody think the best way? So for the YouTube live, I'm surprised that this is coming up a problem, but definitely it doesn't seem like worth it. So I'm gonna end the stream, then go back to the Zoom just for now. Okay, so I can end it now. Then I'm gonna switch the video feedback to the Zoom at least for that. Although the quality is for now is not that good, but audio is good. Let's do that. So I can end stream. So coming back to where we are, we sort of just want to use the Flory-Hagen theory and to discuss how does different how does the chi parameter relate to the second derivative coefficient. So what we were left at is where we left at in the new slides. We left at where we know that V2 or second derivative coefficient will be related to half minus chi V1. Okay, so I'll make it big and nice that everybody can see. So now, what we have learned in the last few lectures, V2 is second derivative coefficient. It has three conditions, depends on the slope of this osmotic pressure divided by CRT plot. So in one special occasion that V2 can be zero. And everybody knows the physical meaning of this by now, right? So that means we have a Seda solvent. And you should know, if you have this particular relationship, that means chi equals to a half is a Seda solvent. Okay? So I think here the second derivative coefficient is more easy to interpret because it's just a zero. And but chi has to be 0.5 to be a Seda solvent. Okay? In another case, you should have V2 equals larger than 0 if it's a good solvent, right? This is what we have discussed in the last lecture. So if in this case, then your chi, again, you should be referenced to 0.5. It should be less than a half for a good solvent to happen. As you can see, we talked about there's cases where you don't have a thermal exchange, so we also call it athermal solvents. In this case, your chi would be 0. And as you can see in that scenario, your chi 0 is much smaller than 0.5. That means you have a very good solvent. In chi, if it's 0.25, as you can see, it will be smaller than half, then it will be a good solvent as well. But when chi is much bigger than 0.5 or V2 is smaller than 0, then we have a poor solvent. That means the solvent is not that good and chi is very big. Okay? So slightly different between the chi and the V2, but they are talked about the same thing effectively. Chi Flory-Hagen's parameter both discuss the solvent quality with respect to solvent. And it's a parameter that talks about interaction between your interaction between the polymer to the solvent individually. Okay, if you have strong interaction, your chain will repel each other, and they will not be a good solvent. All right, so let's go back. That's something I want to wrap up, and we already have some homework examples, so I won't go into detail how you can calculate out if the solvent it will be good or bad, as well as the molecular weight, if you know the concentration and osmotic pressure. So I saw many of you submitted the homework today, so that's good. I'll give more feedback to you individually, see if you can get this problem correct. But effectively, what you need to do is just to plot osmotic pressure divided by CRT. Just give you the y-axis, and x-axis will be a very simple concentration. And using those relationship, you just need to do a linear line fit that will allow you to fit the intercept with the y-axis. So that will be 1 divided by n, m as molecular weight, and slope will be should be v2. Some of the textbook call it b as secondary coefficient. So if you see b, don't be surprised. And you can calculate what is v2, and in this case, v2 is going to be a very small positive value, and more importantly, this question asks you to calculate the number average molecular weight, and this will be the intercept and take inverse. You will be able to calculate the molecular weight is about 20 kilodalton. Oh, okay, so that summarized our current discussion about osmotic pressure, secondary coefficient, as well as many related parameters. Any of you have questions related to osmotic pressure chapter? This is a good time for you to ask questions. You can unmute and ask if you have any.
I have a question, sir.
Yeah, Brian, please.
The point of the derivative, and we ultimately arrived at an equation that would help us decide if a solvent was good or not, but what was the point of linking it back to, like, say, the Florey-Hagen's definition of Gibbs free energy change?
Very good question. While in the polymer physics community, there, as you can see, has two approaches to address the problem. And one is the classic way that Florey-Hagen has did this. The other is when you take a thermodynamic approach by itself. So they arrived at two different parameters. One is called secondary coefficient. The other is chi, and they are both able to describe what is the solvent quality and interaction with the solvent. So it's naturally people want to link these two. And what we showed at the very beginning, it's very short, although I'll give a full video to show everybody how to do the complicated math. And that allows you to link those two together. That means you will be able to link a parameter of chi and versus a B2 term. And this is significant. This is significant in the sense that you were able to get what's the value of these two. Okay? All right. So at the end of the day, they are described in the same parameter, but when people first start to talk about them, there is two different ways. Okay? All right, let me do one thing. I do see the microphone is kind of not in best shape. Okay. So, more questions? Anyone?
Would you expect us to know how to write the derivative to link the two formulas together, link the two factors together?
I will do immediately after this class, so you will see it today. Okay? And
Okay.
it's quite math heavy. There is quite some
Okay.
derivative.
So
And
yes, understand it, just don't necessarily memorize it.
sure. Again, my philosophy approach to these long derivative is you don't need to be able to memorize them. It's not worth it. But you should know where to refer to the resource, and you know why we do such math operation and what's the link between different parts. Okay. All right. So next part will be more exciting. If there's no more question, I'm gonna move on. So the next part is the phase behavior of the polymer. So let's think about this whole chapter, as we talked about up to now, is talk about if a process will happen spontaneously or not, right? So we discussed almost every single term in the context of the Flory-Huggins theory. And what Flory-Huggins theory is tell you at a given polymer and solvent combination, either 1% of polymer or 100% or 50% or any ratio you want to pick, will they mix or not? That's a question what we have been trying to pose at the first half of the lecture. So the answer is quite simple. It's going to be mixed or not mixed. And in today's lecture, we're going to talk more details about if it's mixed, that's good. Then you're going to have homogeneous solvents with polymer dissolving. If it does not mix, what's going to happen? And more importantly, as we showed in one of the lecture, your Flory-Huggins parameter will change depends on the temperature. If you have temperature raise or drops, then you would have a different Flory-Huggins parameter chi. That means even you have the polymer might dissolve in one temperature, it may precipitate it out in another temperature. Okay, that makes sense because if you have a polymer, and most of the polymer tend to improve solubility with increase of temperature, and there's a reason behind it, and we will explore the particular topic in here. And before we go into detail, we need to define a few terms that will help you to understand two behavior. And it's a little bit jargon. We're going to discuss in more detail in polymer physics. One is called spinodal decomposition. The other is called a binodal decomposition. Those are different buzzwords in the phase diagram in the polymer community. And by the end of it, you will learn what they mean and how they compare. However, the first part is the phase diagram. So what is a phase diagram and what is phase behavior? And we know what is driving force for the material to phase mix and what is not. And that's related to the Flory-Huggins parameter as well as fundamentally the free energy delta G. And there is, generically, we want to show that you potentially could have an energy diagram if you consider a brick is sitting on the table. And we want to define a few positions and their physical meaning. So let's use this textbook. There is three cases. One is called unstable. If we have a book is tilted at the angle, if I let it go, it will drop, and that certainly is not a stable state. And there is also a stable state. That means I'm going to lie the book very flat on the flat surface, and no matter what angle I disturb it, it will always return to this particular position. If I tilt the book a little bit in both ways, it's just going to come down in the same position. And there's one more special case called metastable. What this means is at this particular positions, if there's no external disturbance to the book, it will be very happy and it will be sitting here forever. But if there's local disturbance in it, and this disturbance could be a tiny force where I poke the book, I don't want to let it fall so rapidly, but you can see it not be able to respond to it, and it will return to the lowest energy state. And this can be seen in this tiny paragraph where you have energy potential for the system, for the U, and you have different angles defined in above. There's two key features here. If some item is located in the bottom of the well, as you can see, no matter where we go, this is always going to be the lowest energy point of the system, and you would always relax things back, and this will be called stable state. That means everything will be stable here. And if you have anything along the curve, then it will relax back. And this is unstable state. So this equivalent to where I have a book tilted at an angle, and whenever I let the system to relax, it will go down to particular energy. Okay? The last situation for metastable is you have local minima. What local minima is saying is here. I'm going to use a triangle to show you. And this local square, it says at this state you are locally stable. What that means? If I move it to left and right a little bit, it will relax back. But if somehow I moved it to here, then it will relax to even lower energy state. So we call it metastable. So in other words, if I poke it so gently, it will be able to relax back, because we only goes up energy well a little bit until I poke it too much, then it will lower to even lower state. So why when you talk about those three different states, in polymer solution we actually have similarly the three different states. They are comparable to those unstable, stable, and metastable states in the phase diagram. If the polymer is in the metastable, it's actually will be able to stay there longer. If it's in the unstable state, then it will phase separate into two different polymer and solvents concentration. Okay? And as I mentioned, those are the phase behavior as we will talk about in today's lecture. We have three different regions from top to bottom. Let me zoom in. I know some of you will have problem to see the text. In the top, it says unstable state. So in this region, if you have a particularly concentration and temperature, let me go back to here. So this is what called a phase diagram. Please pay attention to what the axes are. You have x-axis where is phi2, and that's concentration on polymer. So this means you have concentration from low to high. It can go from 0 to 1. 0 means it's purely solvent. There's no polymer in there. You can up to 50%. That means half, or you can have 100% phi2. Just a volume fraction of the polymer. Okay, and the other axis is T. T is temperature, and as you will see, we will show there is a solid curve and there's dashed line. These two lines are spanning along this particular phase diagram. And how do we read the phase diagram? We have two ways to read it. First is to understand what is different phases here. And as we mentioned, there's one phase shows in the top corner. There's two phase shows in the shaded region, and particularly two phases is going to be within this dashed line. Okay, in the binodal, in the gray area, this is particularly the metastable states, where you could have you can stay at the binodal state. It's metastable. If you don't give it any disturbance, it will be happily sitting there. Pretty much like the book I showed if sitting vertically. But if there is some disturbance happens, if you somehow has a excitement for the local, for example, a shake or any external force to there, then they were able to phase separate into lower energy state. So then the binodal state could continue to phase separate into two different states. Okay? We will talk about more about what is this, what defines binodal line and what defines the spinodal line, and likely in the next lecture. And there's one more point is a stable state, and there is critical temperature we call TC, which is on the top of this curve. And if we meet a TC, that means that's a critical temperature that your system will be always dissolved into a stable one phase. As you can see here, if I draw a line above the TC going from left to right, at all the concentrations of polymer from 0 to 1, I always gonna sit in the one phase state. That means I will be always dissolved, and no matter how much concentration I put in, my system is always happy. There's not going to be phase separation. But let's take another case where you have T0, which is lower temperature. If I start with low concentration of polymer dissolved in solvent, it will be happy, so it will be here roughly. But as I put more polymer in it, it will go through the binodal phase and not able to dissolve in the two-phase or undissolvable states in wherever this region is. Then when I further increase the polymer concentration, it will become dissolved again. There's other way you can look at the curve is where you go from vertically from bottom to top, and if I fix a certain concentration, let's say I always choose 60% of polymer. At low temperature, it will not be able to dissolve, but as I move up the temperature, I will go from two-phase to spinodal phase to binodal phase and to one phase, crossing these two lines. Okay? So the question is why a lot of polymer will behave this way. So this is going to be the lecture. We answer this in the context of Flory-Huggins theory. Actually, Flory-Huggins theory will be an ideal case can explain what's going on in this phase diagram and why we should have or expect to see this parabolic shape of the phase diagram, as you can see. Typically behave like this way, and why? What's the reason, and why is that? So there is a quite complex phase behavior, as most of the polymer will fall into these two states, as we will talk about what is UCST and what is LCST. UCST is U stands for upper, and LC in terms of L stands for lower. So upper and lower, this relate to here. The critical point is at the top of the phase diagram, right? We talked about this. We define as critical temperature as TC. In the UCST, what this says is you can see the upper critical temperature phase diagram. So you always see this is going to be appear on the top. And in this UCST, this is where most of the polymer will behave. Where at the low temperature, at the room temperature, it's not able to dissolve. If you heat up, the solubility improves and you will be able to form one phase. And LCST is a little bit more strange, but some of the polymer will behave like that, where it's inversed, where that means is at the low temperature, it's pretty happy to be dissolved in another polymer. But once you heat the polymer up, it will decide to phase separate at higher temperature. And you then have other weird phase diagram because of uniqueness of the chi. In those cases, chi is going to be dependence of A plus B divided by T. And depending on sign of A and B, we would be able to reach those two states. And I'll talk more in the next few lectures. But if your chi is not a particularly simple relationship, you could have all these weird phase diagrams show second row. And it apparently exists in several unique polymer systems. They're not very popular. There may be only a few percent of polymer solvent. Shows example on the left, where low temperature it dissolves. Then if you heat up, it's precipitated out. And if you keep heating, it's gonna. At the low temperature, it's precipitated out. If you heat up, it will be dissolved in here one phase, and you keep heating up, it's gonna phase separate again. Let's continue. And how do you observe the material is phase separated or not? Is typically use a turbidity measurement. Turbid basically means how opaque your system is. In a perfectly dissolved material, typically your polymer chain is very little. And as you remember, those RG are typically on the tens of nanometer, and in most of cases will unlikely go above micron size, right? Micron you typically need is very, very long polymer chain, and very hard to make, if not possible. So polymer solutions are transparent typically if they are dissolved well. But if phase separation happens, that means you would have phase separated aggregate. Then your polymer chain or these phase separated region can go above micron size. And as you know, some of you know that at this length scale, your polymer, those phase separated morphology can diffract light. That means it will behave turbid. The reason is that the light hits your polymer solution, and the light being reflected or diffracted in various different directions, then it looks like very turbid. A great example is actually milk. The milk you drink every day is oil dispersed in water, and this behaves like turbid. This would be a very easy way for us to see when your polymer phase separate and how they phase separate. So a very simple experiment is you basically have a light source sit on the left side of your polymer solution. I'm going to use our remote again. So you have the light pass the polymer, then there's a photodiode on right hand side, then you just measure how much light is being seen. So if it's a one-phase system, you're going to see 100%, near 100% of transmission of your laser, as you show here, where TR means the transmission of the light source, and in the bottom we have different temperature. That means what the temperature of your polymer solution is sitting at. You can dissolve the polymer at different concentration from very low, 0.14, all the way to fairly high. Here is the weight fraction, and here is concentration. And you were able to plot this as what is the temperature and when your material start to behave like two-phase and phase separate. So on the left, this is going to be the one phase, and if you look at lowest concentration, red dots, it's able to maintain always one phase even at high temperature at 80 degrees Celsius. If you look at middle example, let's take the purple one as data. You will see when you start increasing temperature, you start to have the phase separation, your turbidity increase or transmission decreases here. And in the more extreme case where you have 20%, then it starts to phase separate at a much early temperature. You can plot this particular data here. You can look at the transmission data versus different concentration, and this is what you would see. So you now have a way actually to measure the phase behavior. So apparently people has did a lot of measurement for polymer in different solutions, and they are combining this particular measurement with respect to different with respect to what is theory has been able to provide, and they were able to compare these two and trying to understand what's going on. Okay, so here is what we're gonna do finally introduction about phase diagram and how we understand phase diagram. Okay, so what we're gonna show here is first is we need to consider the phase diagram in the context of the Flory-Hagen theory. So all the data is going to be related to if they're going to phase separate or they're going to mix is only one dimensional. They are all related to the delta G. If the delta G is shown in this particular curve, if it drops with respect to different concentration, then they're gonna either phase separate or not phase separate, depending on specific data and specific curve. So look at this one, where again x2 is going to be polymer concentration. So at different stage you would have a different shape of the curve, and how this particular delta G dependence of x2 will determine if your phase diagram would look like. Okay, so let me add one more slides and explain how we were able to achieve different phase diagram. So let me exit and insert a few slides here. Oops. Okay, so I want to emphasize one thing is first we need to have a quick review of what we talked about in the Flory-Hagen series. So delta G divided by RT is we know. Let's use the lattice series as a very simple one to discuss. Then we're going to go into the Flory-Hagen series, okay? And this last term is chi. The other, you have x1, x2. x1 is the volume fraction of your, particularly your polymer. And we know that you have a contribution of entropic term and enthalpic term. So the first part is entropic term, right? Entropy, if we plot a minus delta SMR, what this does is show you what the entropy would look like depends on what is x2. x2 is basically volume fraction. We know it's will look like, my drawing is pretty hard. Pardon me for that, not the perfect symmetric shape. But this basically says if you calculate what is delta S with respect to the x2, you can use the equation and do it. If you assume x2 is going to be 0, then you're going to have equation above shows x1 will be equals to 1 and ln 1 plus 0 ln 0. And this is going to be 0. And the minimal, the highest the drop in the free in the entropy is going to be happening at a symmetric mixing of 50% of polymer A and 50% of polymer B. So this happens at 0.5 ln 0.5 plus 0.5 ln 0.5. Or this exactly will be ln 0.5. And if you walk around how much concentration of your small molecular B in another small molecule, that would be the shape of delta S. Okay, it will be almost a nice parabolic shape. And how about the delta H? Let's also plot delta H. So this particular term will depend on x1, x2, and chi. Chi will be a constant if you already picked a polymer or two solvents or whatever. Chi will be a constant no matter what you put in. But this particular shape of your delta H curve will depend on your particularly your sign of the chi and as well as what is x2 value, right? So let me show you a few examples. So this curve, if chi is positive, will show a negative parabolic shape of the curve. What this means is you're going to be finding a highest point at the center, and you would have other points at different locations. And please pay attention, this will have a temperature term encoded there because there's RT. So at different temperature, now you would have a different delta H divided by RT. So let's show two examples. One is, what if we have system at low temperature? You would have a curve looks like this, almost symmetric to the bottom, but because we divided by a constant temperature is smaller, you would have a higher value. Okay, so this would be 0, and this would be the high temperature. And we will come back to what these particular points means and why we care about that. Okay?
I have a question, sir.
Yep, Ryan, please. Brian, please go ahead, ask your question. Yeah.
Oh, I'm sorry. It seems like you're adapting the It seems like you're adapting the regular solution theory rather than the Flory-Huggins theory because you're using mole fractions rather than volume fractions.
Yeah.
Did you mean to do that? I thought you just said Flory-Huggins earlier.
So we're gonna do again use the lattice theory first. Then we're gonna go back to the Flory-Huggins in the later part. Again, the reason is very similar to what we did at the beginning of lecture. It's much easier to discuss the lattice theory because you will see the Flory-Huggins phase diagram will not be symmetric and more complicated for beginners to understand. So we're gonna again take a simpler approach, discuss the lattice theory first, then we're gonna jump back to the Flory-Huggins theory at the end of it. Okay?
Yes, sir. Sorry.
So what we were left was talk about what is for chi parameter, what is delta S parameter, and as you will see, those two parameters are important because we need to consider how these two are combined. If we added a one on the top of the other, depending on temperature, you could have different values of delta G. If at low temperature and high temperature, on the turn left, it does not depend very much. But if you combine the last two curves, you would have at a high temperature, you would have almost a perfect parabolic curve, and in the low temperature, by adding these two together, you might have a local maximum. And the why this happens, as I explained in the last slides, because at low temperature, your entropy contribution, the low temperature entropy contribution will start to become more and more significant because there's temperature turn here. Well, the delta SRT does not have it. So this is what you will see. What happens in the delta GM divided by RT at the low temperature, you could have now two local minima and one local maxima. Well, in the high temperature, you only have one local maximum, one local minima, not maximum. So that is the reason you're gonna see all kind of different behavior at low temperature and high temperature. And we're gonna begin one more discussion about what happens if your polymer sits here or here or here in those three special cases. Then we're gonna finish today's lecture, okay? So what's your guess, Brian? If your polymer is sitting here, will they be happy?
You mean at high temperature?
In the high temperature in this particular.
No, sir.
It will not be happy, and why?
It's below ideal conditions because in this case we can assume, like, for instance, for it to reach that value, we can assume a chi value. We can assume an interaction parameter less than. We can assume an interaction parameter, I think, is less than 1/2.
Not exactly right. And in this particular case, at high temperature, let's say this will be 30%. Okay, I picked a random number. So if we say 30% of PS polystyrene in toluene, and just give you some idea, will this be stable? And you said no, because the chi is
Chi has nothing to do with this, does it? Not necessarily. It's not a variable factor here, is it?
It is. Chi will influence the sum of the data, but chi will not directly impact the results. What chi will do is to only influence one temperature, but not every temperature range. So let's try another way to think about the problem. Is someone have another way to give a little bit of thoughts? A second volunteer might want to tackle this problem. Think about delta G.
delta G negative or not. Delta G here is negative. Delta G here is negative, therefore it's spontaneous, therefore it's favorable. So in this case, if that point represents if this delta G is negative or below 0, then a solution would likely to form, then would be considered favorable.
Yeah, that's what is gonna happen. So that's good. It's more a good answer to what happened to the phase diagram. So let's go back to particularly here. So if your system choose to phase separate, there's one law it cannot break, is we cannot move down to the phase curve. Let me go back to here. We cannot say I just gonna go here because that's lower energy state. Then I'm gonna have a lower energy delta G here. Why? Let me explain to you why you can't just say I'm gonna go to this value of the energy point. The reason is if I go there, what that means, the phi 2, this let's assume it's symmetric, so that's gonna be 50%. I cannot have 50% in toluene phase separate into another phase. Why? The reason is simple. We cannot magically get more polystyrene, right? We cannot magically get polystyrene. What this says is I cannot magically make a 30% of concentration and go up to 50 without doing anything to the system, without causing some problem, because conservation of mass is a universal law. If I want to do this, that means I need to create equally a 10% polystyrene in toluene somewhere. If I have two layers, top layer is 50%, bottom layer is 10%, then that's feasible because we split it 30% into two different solutions. And now, Brian and all the classmates, what you need to compare is the delta G. What delta G need to be is to consider what is before is 30% of PS in toluene, and what delta G after is talk about what is a linear combination of 10% in toluene and 50% in toluene. Okay, right? So we need to compare these two. And there's a very simple way, as we show here. When you phase separate from this particular M, you would always phase separate it into two layers. One is higher in concentration, the other is lower. So that's going to be a high concentration layer, a high C, and this is going to be low C. And it will behave into two phases. One is XA, the other is XB. The question where it phase separates comes down to the free energy before we have it as M star, after we have it, before we have M, and after we have M star, and how these two compare. It turns out to be the system free energy before is just going to be where this sits, so right here. And after phase separation, it's going to be a linear combination of these two data points. If you draw a line, and the middle point of this line is going to be the free energy of the system after combining free energy of what this one is had. We can call it NA star, particularly because it has A concentration. So this is going to be at MB star at B concentration at XB, and this is going to be original concentration. It's just going to be linear because conservation of mass. And now the question is, will M star higher than N or will M star lower than N? This defines if your system will phase separate or not. So Brian and the rest of the classmates, look at here. Your M star sits at a higher delta G than M. That means if I have 10%, 30% of polystyrene, if I phase separate it into 10 and 5%, I actually raise the free energy for the system, going from 30% one phase into 10, 50% two phases, M star. So that means that what? It will not phase separate, right? It will be more happily sitting here as one phase. Okay? Then the question for you guys is, in what phase diagram or delta G plot you will see it will prefer to phase separate. It will not prefer to stay where it is. I'll draw another example. So we saw that if you plot delta G, if it's concave up, no matter where we want to phase separate into, let's say 2 data points, if we draw a line, it's always going to be raising the system energy, right? No matter where it is. For the spontaneous phase separation, you need to inverse the delta G curve. That means if I have, again, let's use another example. Let's use polystyrene in water. This would be an ideal case because they're not going to mix. If I have 30% of PS in water, and it will, if you calculate the delta G based on X2, based on the Flory-Hagen series, we know that, right? You know the equation. If you know the chi, you can basically calculate what the delta G and X2 is at a given temperature, at fixed T. Temperature. There is nothing unknown, so that's why you can calculate each dots and combine them into your delta G line. And if it's phase separate into 10%, and again I want to use 50%, you will see the linear combination in terms of free energy. What we have used is M star versus M. This will go down into the free energy. What this means? Now, in this scenario, your system will like to break into 2 layers of material. One is higher in concentration of polymer, the other is lower. That's why you kind of see those 2 data points, 10 and 50. Okay, so we're going to come into the first conclusion for the phase diagram. We're going to define what is stable state and not stable state. Based on this particularly Flory-Hagen series and phase diagram, right? And everybody should know how we plot this delta G versus the X2 plot. As you know, what is Flory-Hagen's parameter? It's very straightforward. So how do you define mathematically if your system will be stable or not? This is a question for the class.
It'll be stable if the initial energy state, if the initial energy state if it's more stable in a mixture than it is phase separated.
I'm more asking everybody to think about mathematically how do we define this particular stable and not stable state based on Flory-Hagen series. So how about they share one common stable state is your curve always concave upwards when you look at delta G. If it starts to behave concave down, then you would have become unstable. So mathematically definition, we can define delta G. Take a second derivative at a constant pressure and temperature. If it's larger than 0, we will see at any data point on this curve it will always concave, because second derivative is basically defined if your curve will be a parabolic facing up or facing down, and this will be defined as delta G mixing in terms of energy. Take a second derivative, if will be at a constant pressure and temperature if it will be a negative value. Okay, so with compare those two, you will be able to define if your system tend to phase separate or tend to phase mix. We're gonna stop here. In the next class, we're gonna do one more work, is to combine or convert what is delta G curve to phase curve. I'm gonna stop here. I want to show one more thing. This is a delta G curve, as show. Everybody can see it on here. Oops, let me make sure I open up slide. And the question is, how can we link this particular curve to a phase diagram curve? Remember, the x-axis is the same, either x1 or phi2, it doesn't matter. It's basically defined differently in lattice or Flory-Hagen series. But in one case, we defined a delta G. In phase diagram, we always have temperature. And what's the link between them? What's the similarity between these two plots, and why we should care about these two plots is what we're going to talk about in the coming up lecture in next Tuesday. Okay, so, and thanks everybody's attention. We're going to come back again next week, and keep in touch. Any question for now? Forgot to ask. If you have question, you can ask.
Like bookkeeping question.
Zoe, please.
Yeah. Do you know roughly when our next exam is going to be?
I can look up the schedule, and we can discuss it in the next lecture.
Okay, perfect.
I think roughly it should be about 2 weeks or so, roughly.
Okay.
Because we need to go through the homeworks, and we need to finish the lecture in 1 or 2 lectures, so effectively in about 2 weeks. Okay? Any more questions? Okay, if not, then let's close today's session. Then we will reassemble next time. Okay, thanks everybody.